Who wants to hear more about Kubernetes? All right, we'll try to make it not. We'll try to make it interesting and add a few more friends to the party. So I'm going to talk to you about how I tested. It's my own personal experience about testing Kafka replication using the tools of Kubernetes, Go, and a few other friends. So that's it. I'm on Tavory. I work at AppsFlyer. I work on a project called Multi-Region, which essentially takes the workload done on a single AWS region and spans it across the globe in multiple regions. I also have, so you can find me at these addresses on Twitter, Gmail, and Facebook. I have my own podcast, Reversing Platforma. If you're interested, it's in Hebrew, about software development. That's it. A little bit about AppsFlyer. So, who here has AppsFlyer installed on their mobile phones by show of hands? Right. Who has mobile phones? All of you probably have AppsFlyer right now on your phone, probably 5 or 4 times at the minimum. Let me tell you a little bit about AppsFlyer and what we do, and you'll see the context right away. So AppsFlyer is a data collection platform. We have SDKs installed inside mobile apps. AppsFlyer is installed on probably something like 80% of the mobile devices or 80% of the Android and a bit less on iOS. But it's a fairly popular SDK. And we collect this data and analyze that. Just to give you a sense of the size of that, so every time a user opens an app that has SDK, the AppsFlyer SDK, an event is sent to our servers. Every time a user does this or that operation, assuming the app is interested in this or that operation, we get an event. And we get a lot more than that. So all in all, it sums up to about something like 90 billion events per day, give or take. So that's a lot of data. And this data is being transformed, transferred, and marshaled into Kafka. So that's why we're so interested with Kafka. So my particular test case was about replicating a subset of this huge data set. We're not going to replicate all of that. So replicating a subset of this data set between 2 AWS regions, one in US East and the other in EU West, e.g. Virginia and Ireland. And while doing so, we want to make sure that data is transferred correctly, that we can measure latency and it's in a good place. And we, of course, want to, we want to make sure that we're able to handle various test cases, or should I say failure cases, such as broker crash, cluster resize, packet loss, and things that happen in reality. Now, does this sound familiar to any of you? Broker crash, cluster resize, network partition, etc. If so, then it's no coincidence. Some of you might be familiar with the series of blog posts by Kyle Kingsbury called Jepsen, in which Kingsbury takes a certain database and more or less tears it apart, kills this host, drains that node, etc., and tests until it breaks. So my inspiration to working on this project was more or less this series of blog posts in which Kingsbury automates everything, automates the test case. So what I imagined was, how do I create this kind of workflow in which anyone can later test Kafka replication with perhaps newer tools that were created after my initial creation, and can run the same test cases with those tools and make sure that everything works or doesn't work as expected. Now, originally, Kingsbury wrote his or at least most of his scripts in Clojure, And Clojure is a language that we're pretty much familiar with at AppsFlyer. It's the main backend language at AppsFlyer. However, in this case, I decided that Kubernetes would be a better use, would be more fit to this case. So eventually, no Clojure code was harmed during this experiment. I did write some code in Go, and we'll get to that later. All right, so a few words about Kafka. Who here is familiar more or less with Kafka? All right, so just a few words about that. So Kafka is a stream processing system. It's built on brokers. Brokers are actually just nodes. So it's more or less, so it's something between as a queuing system and a database. Okay, so you might sometimes refer it as a database and sometimes as a queuing system. The brokers are the actual nodes. You write messages to topics, and the topics are composed of partitions. Partitions is Kafka's way of scaling things, of scaling out. It's like shards in database. So how does Kafka get replicated in high level? So there are several tools to replicate Kafka, and my goal was to actually test some of them. And all of them take more or less the same approach, and this is taken from the wiki of this project. My project is actually open source. You can go there and download and run it, and you might succeed. I hope you will. But in high level, what we see, so we see 2 data centers, right? Oh, you can see that. Anyway, you see 2 data centers. One has the source Kafka, and the other has the target Kafka. And you have a replication process somewhere in between. Now, the replication process could run in either data centers, either the remote or the local, or it could run between. Most of the systems recommend that it would run in the destination data center because of various reasons. So that's the basic setup. Now, how do you test that? So this is how you replicate Kafka, but how do you actually test that replication works as expected? So to do that, I created a dedicated producer and a dedicated consumer. Those 2 were written in Go, and they create the load. So the producer produces messages, the consumer reads them and validates correctness and completeness and latency and all that. And we'll get to that a little later. So I mentioned some of that before. While doing this project, it was a point for me to be able to document everything so that if I return the next day, I remember what I did. I could very easily send it to my friends and tell them to just run it. So the best way of documentation, as I know it, is just code, right? We also want reproducibility, and again, the best way of getting reproducibility is with code, and we want to be able to monitor everything very closely. Obviously, we just do it with code. So although this file, this project has a README file, the README is very high level. Everything is documented in code, and that was my goal in that. Now we enter Kubernetes. So I think that in this forum, we don't need to dive deep into Kubernetes, so I'm not going to do this, and we're not going to do this brief introduction. We're not going to speak about the cluster manager, the nodes, the pods, deployments, stateful sets, etc., because I assume you all know that. Eventually, what we get in this project is a makefile, because I like makefiles, so a lot of that is scripted over make. That has various targets, and the main target is make Kubernetes all. And while running that, what you get is the following. So you get to provision virtual machines in AWS in both data centers in Ireland and in Virginia. We set up VPCs, we create security groups, load balancers, we install Kubernetes, we install monitoring with Prometheus and Grafana and a few other interesting friends, etc., etc. So, and yeah, and eventually, we installed a replicator. There are several kinds of replicator. In this session, we're going to focus on uReplicator. uReplicator is a replication tool by Uber. That is the main tool that I tested. All right. So underneath the hood, we actually use kops. I'm sure most of you are familiar with kops. And this is how you create a 40 nodes cluster with kops, just as an example. And eventually, we get the following setup. So we have the 2 data centers, and in each data center, we have something like 40 or 50 nodes clusters. In each cluster, we have 30 brokers, more or less. That's just my test case. Of course, the numbers may vary. And we have the replicator workers that copy the data from one Kafka to another. And we have the producers and the consumers, which are the codes, my Go code that actually runs all the tests. It's US East 1 and EU West 1. So Ireland and Virginia.
Just to clarify, was you running Kafka inside the cluster or just Kafka?
Yes, Kafka is inside the Kubernetes cluster. Actually, everything is inside the cluster. Performance-wise, it might not be the best choice, but it was just easy to set up. I didn't, for example, initially I started working with attached volumes. Then I gave that up because it's just easier not to use them. And for my test purposes, it just wasn't required. So latency as measured between the zones is something like 70 round trip, 70 millisecond round trips. But my measured latency was a bit lower than that, actually. But you know, it varies, it depends. And if you have a dedicated VPC, which in this case I didn't, but if you have a dedicated VPC connection, VPC peering, then it's even lower. All right, so eventually after running all that, you get this nice output. That's okay, you don't have to read this. But it just gives you a few links to useful resources, such as a Grafana dashboard that's pre-populated with the dashboard, Prometheus in both sides, and WeaveScope, which is a nice tool. Maybe we'll look into that a bit later. So this is how the Grafana dashboard looks like. And all that is generated automatically by the make command. So for example, what you see up here is the traffic in and out of those Kubernetes clusters in megabytes. You see here you see the producer and the consumer traffic. Here you see a general overview of the setup, and here you see the latency as of this point, for example. So that's just part of the dashboard. I installed WeaveScope. I discovered WeaveScope, which is a very neat tool. It's sort of like top for your cluster. So you can see processes, you can see pods, you can see networking, and all that kind of interesting things. It's very neat, very nice. It does take some resources. So I mean, it's not for free. And this is, for example, it's a network view, in which case you see, for example, you see 29 brokers, 29 Kafka brokers working with a zookeeper, and they talk to the internet, and you have the kafka-mirror-tester producer in this case, 10 pods, sending information to those brokers. So that's pretty much what you'd expect from this test case. So WeaveScope is a very useful and nice tool that I would recommend. And of course, you can run kubectl, which is the lower level tool. Now let's put all that into test. So we have the clusters running, we have the producers, we have the consumers. Now let's start messing with them, right? Let's start killing things, let's start breaking things and see what happens. All right, so the first fun activity for today is killing a broker. So a broker, again, is just a Kafka node. The clusters consist of something like 30 brokers. sometimes brokers may die. So my goal in this test is to make sure that first latency doesn't go up too much in this case, and second that we don't lose data or we don't get repeated data and things like that. So the way to do that is it's quite easy actually. Since we're using Kubernetes, we're just going to do kubectl delete pod. What this actually does is delete this pod. By the way, you could see that this pod is, since it has such a nice name, it means that it's a stateful set. So for Kubernetes, I actually used a stateful set. So what this command actually does, it kills a pod, but then Kubernetes notices that a pod had been killed, and it revives it. Okay? So let's see what happens. We look at the dashboard. It's maybe it's too small, but I'll explain. So here's the point when we kill a pod. We do see some slowness here, but eventually everything back to normal after something like 5 minutes or so. And we didn't lose any messages. You can see it here, but I tested. None of the messages got lost. So we have a check on that. Good. Next interesting test case, resizing the cluster. Sometimes you want to increase or decrease the size of the cluster, and we want to make sure that nothing breaks here as well. Again, you do that quite easily using kubectl. In this case, we tell it to scale the stateful set called Kafka source, and we decrease the size. It was 30, now it's going to be 29. So it looks more or less the same. The size gets smaller. We see a small glitch here in latency, but it's not too bad, and eventually everything is caught up, and none of the messages got lost. This is due to the fact that we had replication in Kafka. If we hadn't had replication in Kafka, then we would have lost messages because one of the nodes just, vanished. But we did have replication in Kafka, and that was intended, so we didn't lose any of the messages. Okay, next interesting use case. Sometimes you want to increase the size of the replication cluster, right? So again, we do that by kubectl scale deployment. In this case, your replicator is not stateful, it's stateless. And we increase the size to 9, and let's see what happens. So what we want to make sure here is that the new worker takes some of the load. And this is what you see here, the yellowish thing down here. So here you see only 8 workers, and now you see the 9th worker joining. So that's a good thing. That means that your replicator understands that there's a new worker, and the load is distributed between all workers. And again, no messages were delayed or lost in this process. So again, we have a check on that. Kafka does not use attached volumes, but it does persist to local disk. So as long as the disk is there, then it's okay. But specifically now, I'm looking at your replicator, the replicator itself, and I want to make sure that, and the replicator itself is sort of stateless. It has some state in its own zookeeper, but the workers themselves are stateless, and I just want to make sure that they're able to distribute the load dynamically. Okay, another interesting use case. Sometimes I want to add a new topic. To do that, I tell my test code to start writing and reading from a new topic, and this is how it is done. And what I want to check here is how fast the replicator discovers this new topic and starts replicating. So the blue line shows you the new topic that's being created and written to. In this case, it's 200 megabytes per second, twice the capacity that I wanted to test. And after something like 2 or 3 minutes, you see the replication process starting. The sort of orangish and yellow lines. So we see there's something like maybe 3 to 5, maybe 4 minutes after all data is being replicated, and that's good enough in our use case. And maybe the last use cases. The last use case is if you have any experience working with Kafka, you'd know that changing the number of partitions is somewhat of a delicate operation. So I want to make sure that if I do that, nothing breaks. So to do so, I shell into one of the Kafkas and run the command Kafka topics, alter topic, minus minus partition 300. It used to be 150, and now I double it to 300. And I want to make sure that your replicator is indeed seeing this operation and starts to replicate the new partitions. Unfortunately, it doesn't. So that's an interesting thing that I learned. So it turns out that your replicator does not know how to do that, and I had to tell it to do so. To do that, I again, so in this case, I create a port forward, and I send HTTP commands to delete the topic and then recreate the topic. So that was something that was important for me to learn, and I'm happy that I learned this before going to production. Okay, and really the last test case is packet loss. So everything that runs across the Atlantic surely will lose some packets, and we know that's going to happen, so why not simulate that? So to simulate that, I used with scope. In this case, the interface that you see is with scope, and you can simply go to a certain pod and tell it to start losing packets. So that's quite nice. In this case, I think it was 10% packet loss, and 10% is actually quite a lot. So we expect to see something bad going on here, and let's see what happens. So indeed, you see quite a dent in traffic. And but once, so that's what happens during packet loss activation, and now we deactivate packet loss, so everything's back to normal, and you see things catching up. But there are quite a few bumps here, so we know that it's going to be difficult with packet loss here. This is more or less expected. What was important for me to make sure is that we're not going to lose the data. So it's okay for data to be late, but we don't want to lose this data, and indeed, the data wasn't lost in this case. Okay, so this is so much fun, right? Taking a database or taking a queuing system and breaking it down. But how do we actually do that? So let's have a quick look at some of the code. It's definitely not going to be everything, and we'll be done with that. So there are two parts to code. One is the Go producer and consumer. The other part is the Kubernetes part. Let's have a quick look at Go. You don't need to know the language. I don't need to understand this. Just a few interesting concepts. So this is the producer, and this is the main loop of the producer. So what we essentially do is we loop endlessly, and we generate sequence numbers, and those numbers are used in order to validate that all messages had been received. And this is the consumer loop. The consumer looks for more data, and it also listens to some interesting events. And once a new message had been received, we process it. So processing means validating the sequence, collecting throughput information, and collecting latency stats. So here's an interesting question. We said we have 10 producers and 4 consumers. Now, how can the consumers validate that all messages had been received? How would you do that? So each consumer runs in its own process, but how do you know that none of the messages got lost? Okay, so if we had just a single consumer, we could have an in-memory data structures that, you know, a listing of which messages we received and which messages we didn't. But we don't have a single consumer. We have 4, maybe 5, depends on the capacity. So one other way to do that is maybe use an external memory, right? Something like Redis, maybe, or DynamoDB. in which you could have that listing of which messages had been sent and which messages had been received. But this is also quite involved, and I didn't. Well, initially I went there, but then I decided I don't want to go there. So eventually, I found out that there's a trick with Kafka. So Kafka holds the promise that within a certain partition, if you provide messages certain keys, then it would ensure that all messages with the same key would go to the same partition. So this is sort of the secret of locality. So you could have the consumer. Each consumer reads. It has its own partitions. So let's say we have 300 partitions, right? So a certain consumer is responsible for 10, maybe 15 of those partitions, and within those partitions, the sequence numbers are serial. So that's more or less it. So all validation is actually done locally. And this way, if we lose messages, right. And the producer needs to know the number of partitions, that's all. Not the number of consumers, but the number of partitions, and then does mod. So that's more or less what happens here in this code. You do mod by number of partitions, and that's more or less it. Now, of course, the messages themselves need to embed this information inside the messages. So this is the message format. We have the producer ID, the sequence number, the timestamp, and a payload. So we will not have time to dive into Kubernetes, but you're welcome to search the project on GitHub and see for yourselves. There are some interesting concepts regarding Kubernetes, but we will not have time to dive into them today. So 1 minute for questions. Right, so did I test partition tolerance of the Kafka clusters themselves, something like split brain or something like that? No, I did not test that. My main focus was to test the replication itself, not Kafka. So my assumption was that Kafka is okay. Now I just want to test your replicator, so I did not test this. Okay, so eventually we don't want to spend all companies' money on Kubernetes clusters, so we need to delete everything, and a simple single command line, make Kubernetes deletes all, simply deletes everything, and we get this nice output of everything gets destroyed, and that is it. Thank you.